Yo no puedo.
I think it is recording. Yes,
Already
it's recording.
yeah.
So the first talk of this morning will be given by Dr. Reyes Calvo. She's an Investigadora Distinguida, which means distinguished researcher at the Universidad de Alicante in Spain. Her expertise is in the research of electrical and magnetic properties in quantum materials, such as topological insulators and low-dimensional structures. So we welcome then Reyes.
Thank you, Enrique. It's a pleasure to be here. I'm going to share my screen. I want to thank Carolina in particular to invite me for this seminar. And actually, I am now at the Department of Applied Physics, and I'm going to talk about something that it's a work that actually I started when I was at Stanford University. That's where actually I met Carolina in the past. So it's actually a pleasure to have the opportunity to tell you about this. So as I try to convey my abstract, I'm going to tell you a bit about 2D topological insulators, and I would like to highlight some aspects that, in my opinion, some of them, like disorder, have been more addressed in these systems. But I also would like to talk a bit about electrostatics or band modulation, or something similar to band bending in classical systems in this system, something that, in my opinion, has been a bit overseen in this for these systems in the past. So I would like first to very briefly introduce what is a 2D topological insulator. Probably most of you know this already. In the last, for the last decade, condensed matter physics has included a classification of materials in terms of the topology of their electronic wave function, or some properties of the electronic wave function. I'm not going to get into a lot of detail, but basically, in that sense, we can classify insulators like trivial or non-topological, or just boring insulators, where just as usual, the conduction and the valence band are just separated by the gap, and there is nothing special about this. But in some cases, we can get insulators that belong to different topological classes than the trivial ones. For example, if for some reason we get an inversion of the bands, that it means that for some reason the conduction band goes above the valence band, and then maybe, for example, we have a strong spin-orbit coupling that opens a gap, we end with a structure something similar to what I represent here, where the conduction band is valence-like and the valence band is conduction-like. If all the ingredients get together in this material, then is topologically different, belongs to a different topological class than a trivial semiconductor. And when that happens, at the edge of this material, even if the material is insulating, at the edge we get conductive edge states that we call quantum spin Hall states. The canonical material where this was first realized, predicted and then realized, this phenomenology was predicted for graphene, but it was for the first time realized in mercury telluride quantum wells. This was first realized for mercury telluride quantum wells that are strained to the lattice constant of cadmium telluride. When these quantum wells are very narrow, they are just trivial semiconductors. Yes, the conduction and the valence band separated by the gap. But if we make them thick enough, above 5 nanometers or so, then we get band inversion, and they become a 2D topological insulator. And in the very seminal model, the first model predicted by Bernevik and Sang, that now is this model is now at the BSC model. They consider an abrupt transition between the inverted band structure and the non-inverted one. And in that very simplified model, well, they obtain that one should get linearly dispensive Dirac quantum spin Hall states crossing at the middle of the gap, as is represented here. Then, well, these states are the quantum spin-Hall states. They are we have a couple of counter-propagating edge states at each edge of the sample, and they have a spin momentum locking. That, in principle, it prevents backscattering to happen, since to backscatter an electron moving at one edge, we have to flip the spin. And that, in principle, in absence of magnetism, should be forbidden. Or in other words, that what people say in the literature, that they are protected, the conduction at the edge is protected by time reversal symmetry. In absence of magnetism, we cannot flip the spin, we cannot backscatter. However, well, in that very clean, very ideal picture of a 2D TI, while a trivial insulator, when we bring the chemical potential, we bring the Fermi energy across the gap, should not conduct at all. We should have zero conductance in the gap. For a 2D TI, since we always cross the helical states, we should get in a 2-terminal device or in a 4-terminal device, we should get a 2e² h quantized conductance in the gap. The reality, this is a very nice but very ideal model of a material, and the reality is slightly more complicated. First of all, this is the first experiment that was run in the group of Lawrence Molenkamp in Würzburg, and they show clearly how when the material is thick, very thin, excuse me, it's a trivial insulator, and therefore they observe how the resistance goes almost to infinity. The conductance goes almost to zero when they cross the gap of the material. When they look at thicker quantum wells, they find a conductance that is more or less quantized. Please keep in mind that this is in logarithmic scale, so there are quite severe fluctuations on top of the expected quantization. And this is only the case when the stretches of material are rather short, in the order of a few microns. When they make the devices longer, then they observe that the resistance increasing, suggesting that there is indeed. I have to say that this data is from 2007, that the field has advanced, and that especially in Würzburg, they grow now much nicer material, but some of the limitations, they get much cleaner quantization for short devices, but still above 5 or 10 microns, there is backscattering. This phenomenology has been explored also in 2D materials like tungsten ditelluride, but again, above certain distances, backscattering still occurs. So I think there is not such a 2D TI with very long mean-free path up to today. So the backscattering, there are different models that have been proposed to explain the presence of backscattering at the edge. For example, this paper by Varinen and others, they propose that there may be some charged puddles, and some mercury telluride samples are rather inhomogeneous, so it's not crazy to think that you can have accumulations of charged puddles where the electrons propagating at the edge might enter, lose coherence, and basically come back to the edge and with any spin state, and therefore backscatter. But there are other deviations from the ideal predictions of the VSE models, and I will not go into much detail, but we have observed in the past unexpected behaviors with applied high magnetic fields. The group of Boquillon in Paris, they observed some also deviations in the expected capacitance of the material at the edge, or the capacitance associated to the one-dimensional edge states. And sometimes we have observed also that for very short stretches of materials, the conductance goes above 2e²h. This in principle could be also attributed to disorder and perhaps percolation through the bulk of the material, but maybe could also be related to perhaps the presence of extra or other states at the edge, which is something that is not discarded neither in this work of the quantum capacitance. So, so there are different reasons for which the mercury telluride may deviate from the ideal behavior predicted by the VSE model. Number one is disorder, Another one is that when you look into more detail of the electronic structure of the material, for example, using a K.P model that takes into account also finite effects, one finds that, first of all, the valence band is very flat, it has a very high density of states, and also that the crossing of the quantum spin Hall state does not occur in the middle of the gap, but is buried indeed in this camelback of the valence band. And there is something else. As I said, the BSC model assumes that the transition between the inverted and the non-inverted band structure is actually abrupt. It occurs suddenly at the interface, but that transition, in principle, there is no reason to not think that it could occur also in a smooth way, no? And that indeed was considered a long time ago in the 80s by two authors called Volkov and Pankratov. And if you consider a smooth transition between the inverted and the non-inverted band structure, then you get sorry, I'm gonna place you in a different, sorry, I cannot see the side of my screen. Yeah, sorry about it. So if the transition occurs in a smooth way, then you get a spectrum that includes the linearly dispersing states, the quantum spin Hall states, but also a set of extra states that are parabolic and therefore not protected by symmetry. And in recent literature, we call these states Volkov and Pankratov states because they were first predicted by Volkov and Pankratov in this paper from 1985, where they already consider this transition at the interface between two materials, one with inverted band structure and another one with non-inverted one. And if you look at what they obtain in the energy spectrum, is indeed the quantum spin Hall Dirac states and a set of parabolic states. That's just because they consider this transition to be smooth. So this idea of looking at inverted and non-inverted interfaces is actually rather old. It's true that they never placed it in the context of a topological classification of materials, and they did not consider the arguments of symmetry protection, for example, for the conduction at the edge. So that came later with the papers by Kane and Mel and Bernevik, etc. This Volkov and Pankratov scenario of the smooth transition has been considered by Chumakov and others for 3D topological insulators more recently. And well, in case you want more details, two collaborators of mine, Tineke Vanderberg and Dario Versiu, have developed the extension of this model to 2D topological insulators into recent papers that I leave you here the reference in case you want more details. So up to here is my introduction about the limitations of the BSC model for real materials, and a bit of which other models we have to complete perhaps this picture. And now I'm going to show you some experimental results which can be explained if one considers this possibility of having extra parabolic states living at the edge. It might not be the only explanation, but in any case, I would like to highlight the importance of considering this modulation of the bands at the edge of 2D or 3D topological insulators in order to get a complete picture of the problem. So the experimental results I'm going to show are taken by a technique called scanning gate microscopy. I think the speaker after me is gonna talk a bit also about this technique. Briefly, we use an AFM conductive tip, to locally tune the Fermi energy, or locally alter or locally perturb with an electric field a device. Now, this technique has been used, for example, in the past to look at quantum dots in carbon nanotubes, and in that case, any point scatterer gives you in scanning maps. Scanning gate maps will give you information about the position and the size those dots. And these maps are taken by placing the tip, measuring the conductance of the device, while placing the tip at different spatial positions. Therefore, every time the tip is at the same distance of the sample, it creates the same, or the center of scattering, it creates the same perturbation, and therefore you get a circular geometry of the features associated to the scattering center in the maps. So the idea of these experiments is to apply the scanning gate technique to quantum spin-Hall states and see if, when bringing the tip to the quantum spin-Hall states, we can learn something about the scattering occurring at the edge. For that, we prepare the samples by a process of lithography and etching. The important part here is that we define an edge at the cadmium telluride mercury telluride interface. So here we have the mercury telluride quantum well, and we create a MESA with a defined edge. This is an optical picture of the device. The mercury telluride quantum well is buried under this area here. We place some contacts in order to measure transport, and we are going to scan this area with the scanning gate tip. An important detail here is that the material has been grown on top of a gallium arsenide conductive substrate so that we can also apply a backgate. So I have a backgate electrode that allows me to tune the overall density of states of the system. If I use it, I can sweep the backgate voltage while I measure zero bias conductance across these two contacts, and I get something like this, indicating that for this voltage, the material will be slightly n-doped. Around here should be the gap, and when I am -6 volts, the device will be slightly p-doped. As you remember, the valence band is very flat, so the conductance does not typically increase very much in the p side. So now that I have the backgate into action that allows me to tune perhaps the material, let's say, if I go to -6 volts to a slightly p-doped regime, the tip into action. And I can locally create an electric field to perturb the device. And if I do so, and I record the conductance, while doing that, I get this kind of scanning gate maps, where I can clearly see how, in this situation, where I have a bulk that is slightly p-doped, I can tune slightly the conductance when I place my tip on top of the edge. First of all, I see some kind of circular features and rings. Well, if I take the derivative of the map, I see more clearly. I see some rings that increase in size as I increase the voltage on the tip. This is in very good agreement with a previous work in the group of David Goldhaber-Gordon at Stanford as well. And basically, the rings increase in size with the tip voltage, and we see a small decrease of conductance when the tip is above the edge for negative voltages of the tip. And if I apply now a positive voltage on the tip, I see a slight increase of the conductance. So this, in principle, was attributed in that work to the existence of p-type charge paddles. No? If my valence band spatially fluctuates with respect to Fermi energy, or the other way around, I get these metallic regions that are p-type, and they will react in the way I described to the action of the tip. Yeah, I'm not gonna get into much detail here, but that was described in the work by Markus Koenig in PRX in 2015. However, in this work, we were able to tune the backgate voltage. So I can explore now also other situations, not only when the material is slightly p-doped. And if, as I said, the p-doped paddles are expected to behave the way I see here. If the tip has a negative voltage, the conductance as I go over the edge decreases, and if the tip is positive, it increases. Now, when we look at more values of backgate voltage, what we see is that actually, surprisingly, I get a very similar behavior for other gate configurations. And to give a meaning to these gate configurations, what I'm gonna do is take a look at what happens at the bulk. No? So now if we focus on the bulk of the device, no? What I'm doing here is basically applying the axiom of a positive charge tip on top of the bulk of the device. And when we look at that, we see that for positive applied tips, we see this dependence of the central part of the dependence on the conductance when the tip is applied on the central part of the device. No? For a positive tip, I see an increase of conductance, and for a negative tip, I see a decrease of conductance. Basically, the interpretation is that for -6 volts, the bulk is slightly p-doped, so a positive tip decreases the conductance, and the other way around, sorry. For a slightly p-doped material, a positive tip decreases the conductance of the device as it brings the Fermi energy to the gap, and a negative tip should increase it. In the other way around, at 0 volts for the backgate, my material is slightly n-doped. A positive tip increases the conductance of the device, a negative tip decreases it. And I can, according to this interpretation, I can also identify the situation at -4 volts as the charge neutrality point of the device, as I can see that I have barely no effect of the tip on the bulk, on the conductance of the bulk, when I position it on top of that. So for the bulk, everything looks more or less sensible. However, if I perform a similar analysis at the edge, as I said, I observe always the same behavior at the edge, no matter which doping I have in the bulk. No, the edge conductance, the conductance at the edge, the conductance of the device always increases when I apply a positive tip on the edge, and always decreases when I apply a negative tip on the edge. And this, in principle, is not compatible with that interpretation that I gave before of only charge paddles explaining all the features. As I move the bulk Fermi energy to the conduction band, I should see the character of the paddles changing from P to n-dope. Something as I see in the bulk, no, this crossing here, I should see the same at the edge, and I don't see it. And then we got to the conclusion that we need to invoke some kind of electrostatics, some kind of modulation of the bands towards the edge in relation to the bulk in order to explain our results. Also, another feature that we observe is that the areas where the action of the tip is more intense seem to move from the bulk towards more and more and towards outwards the device as I change the bulk density of states, or I switch the polarity of the carriers of the bulk. Possible interpretation from those results come from a possibility that is the existence of extra edge states at the edge of Mercury telluride quantum wells, that we have these quantum spin Hall states, and because as I show in the K.P model, they are buried into the valence band, they give all this space for if the transition between the inverted and non-inverted phases is smooth, then we have a space here for all this Volkov-Pankratov, these parabolic states to appear. And basically, if we consider that, and you imagine that we move the Fermi energy from the valence band to the conduction band, we can have situations while the Fermi energy is still in the bulk, but we get a bit more conductance than just 2e²/h. So that justifies why we observe a slight higher conductance than 2e² for the device when technically the bulk is at the charge neutrality point. It also explains why would explain also why the edges behave as n-dope areas, and why we have a stronger effects as we move towards higher and higher chemical potential positions, since if one looks at the density of states, expected density of states, the spatial distribution of the density of states of this system you observe that as you move the Fermi energy from here from the valence band towards the conduction band, the Fermi energy occupies more and more space. Sorry, the density of states occupies more and more space in this towards the bulk of the device until, well, it enters the conduction band, and you get a high density of states in the bulk as well. So in summary, we took scanning gate conductance maps that revealed that the conductance of the device changes very differently when we position the tip on the edge than when we position in the bulk, that we cannot explain these results only based on disorder, that we need to consider some kind of electrostatics in the sense of considering a modulation of the bands towards the edge. This is just an analogy, but to me, this is the topological analogy to the classical band bending that we often consider in semiconductors when we have an interface of a semiconductor with vacuum or with another semiconductor with a different gap, and we need to align the vacuum levels. So in a similar way, to me, this is the way to consider the role of electrostatics into the topological transition at the edge. And maybe it's not the only explanation for the experimental results, but we think that the existence of these extra parabolic states could also explain other experimental discrepancies, not all, but some of the discrepancies observed in the experimental results on 2D TIs when compared to the Bernevik and Sang, the BHC model. Yeah, sorry, I would like to, that's my talk, and I would like to acknowledge the group of David Goldhaber-Gordon, where I did most of the experiments, the group of Lawrence Molenkamp, who grew the material, and in particular, my theory collaborators at the DIPC in Donostia Physics Center, Tineke van den Berg and Dario Bersu, who developed all the modeling and helped me a lot to find an interpretation for the results.
Okay, thanks a lot, Calvo, for this interesting talk. And now we have a few minutes for questions from the audience. As I said at the beginning, I would ask people to please write down their questions in the chat window so I can transfer them to Reyes, either in Spanish or in English.
Enrique?
Sí.
Sorry, if we don't have questions in the chat, maybe we can start this directly.
The next one, yes, that's probably okay. All right, so there seems to be no questions, so
I have one actually.
Okay, please go ahead.
Yeah, it's so you mentioned this edge behavior you're seeing. It's not only connected to these metallic states due to disorder, right? Structural disorder. So it's connected to electrostatic modulation. But what's the contribution of each? You know, so because if if you have disorder in this 2D topological insulator, maybe you can tune the disorder to, you know, like study how this variable it's contributing to this modulation you're seeing at the edge. So how much of each contribution you think you're seeing in this?
Well, in principle, the disorder should create, I think, point scattering. No, there should be a point scattering, no? And it appears in the experiments as those rings, right? But it's difficult to disentangle the part of those rings to separate that to the other more overall contribution that we seem also to observe, no? And I think it's all connected. And from a theoretical point of view, apparently it's very difficult. You will need to use the KWP model and to do a self-consistent study, no? As it has been done, for example, for quantum Hall, no? Where you consider the you apply a gate, no? If you only consider that the quantum spin Hall states are there, they already are going to screen that gate more than the bulk, because you have some density of states there. So you have to consider a self-consistent problem, no? Like how much the H states themselves screen the applied electric field, and therefore they also contribute, by their own existence, contribute to the modulation of the band structure. So it's not simple to quantify, neither experimentally or theoretically, to my knowledge today. I see a couple of questions here in the chat. Should I?
Please go ahead if you want. You can.
Yeah. So Benoit asked if it's possible to soft-confine these structures rather than etching. The question is, in principle, the answer I think is not, or is very difficult, because you cannot open a gap easily into the etch state. So if you etch away, every time you etch, you get a wall, an interface, and therefore you get etch states there. So confinement is difficult, but there are some proposals. And I have seen only one almost realization of that very recently in tungsten ditelluride, where if you place a magnetic material on top, in principle, you should gap the etch states. And therefore you can confine by using magnetic electrodes instead of electrostatic electrodes. And the temperature is 5 Kelvin, and the magnetic tip, well, you could use a magnetic tip, yeah, and then you could see if you could gap. The effect of a magnetic field should open a gap basically on the quantum spin Hall states, but it is rather small. So I don't know if a tip would create this high enough magnetic field to do it. I think you have better chances by also placing things very in proximity and getting an exchange gap, not only just a straight field. And finally, if I understand what the statistics that you invoke has to do with the fringing field, that's part of it. I think you can think about it in an analogy to the considerations you would do every time you have a semiconductor, right, that is interfaced with another semiconductor with vacuum. No, you have to think about the vacuum levels alignment. You have to think about the potential inhomogeneity of your gate, right? If you apply an electric field, the effect of that electric field at the bulk and at the edge is going to be different. And as I said to Carolina before, also the self-screening of that electric field that the existence of the edge states themselves would create.
Okay. Well, is there any more questions from the audience? I don't see any more in the chat window so far.
I just have a simple question. It's about the fabrication. How did you synthesize the quantum well? What was the technique you used?
Oh, the quantum wells are grown by the group of Lawrence Molenkamp in Würzburg, and they use molecular beam epitaxy.
Yeah.
Right. Well, thank you very much, Reyes, again for your nice talk.
Thank you.
Thank you.
And well, our next speaker is Dr. Benoit Hackens. He's a permanent researcher at the Institute of Condensed Matter and Nanosciences at the Université Catholique de Louvain, Belgium. And his research focuses on the local scale investigation of electronic transport in nanostructures and nanodevices. Therefore, we welcome Benoit.
Thank you. So do you see my screen or?
Yes.
Yes.
Okay. Let me see first. Yeah. Okay. So I'm now full screen. So first of all, thanks to the organizers for for giving me this opportunity to share with you some of our recent results. So today I'm going to talk about scanning gate microscopy. So there are some common, let's say, some common points with the last talk. But I will focus on graphene and yeah, graphene in the quantum Hall regime for this time. So actually, I'm heading a group at the Université Catholique de Louvain in Belgium, where we focus on this technique, so scanning gate microscopy as an imaging technique for charge transport in various kinds of devices. So we have made a series of contributions on more classical, let's say 2D semiconductor heterostructure-based systems in the past. And in the last few years, we have focused rather on graphene. So there are some work that we are doing on graphene at close to zero magnetic field, including probing Klein tunneling. So when the tip is actually biased at high negative or positive voltage, you can actually induce locally NPN or PNP junction in a device, and then you can probe transport in this system, and in particular these peculiar effects of tunneling that take place in graphene. But actually, I rather, so I could have talked to you about that, but I prefer to limit the scope of my talk to quantum Hall and edge states in graphene. So this is, and the good point is that it has also some, let's say, it kind of brings some links with the last talk. So the work that I will present has been mainly performed by Nicolas Moreau, who is a PhD student in my group, and by Boris Brun, who was postdoc until beginning of this year in my group. And the samples have been prepared by Somia Somanchi in the group of Christoph Stampfer in Aachen in Germany, with boron nitride from the Watanabe and Taniguchi group in Japan. Okay, so that's the outline of my talk. So I'm going to talk about quantum Hall edge channels. So you have already heard about edge channels, but these ones, I will start with really simple picture of quantum Hall edge channels in conventional semiconductor-based systems. And then I'll kind of motivate the interest for these edge channels in the perspective of electron quantum optics, which is a kind of new field, well, not so new now, but has emerged, let's say, some 20 years ago, and really is developing quite well now. And then I'll tell you a bit about scanning gate microscopy and how we do that here. And then that will be the introduction, and then I'll talk about our experiment in graphene and in the quantum Hall regime, some data, some consideration about upstream modes, antidotes, and comparison with simulations. Okay, so quantum Hall edge channels. So this is a kind of basic textbook picture of two-dimensional system with a Hall bar pattern in it, and actually the quantum Hall effect emerges as you apply a large magnetic field perpendicular to this system. So this is a two-dimensional electron system. Let's assume that this is confined in a semiconductor heterostructure, and you measure the resistance, longitudinal resistance or transverse resistance of this system just by applying current and measuring the voltage drop either along the current or transverse. Okay, and if you look, let's say, at a specially resolved picture of what happens, then you have to consider that actually at high magnetic field, you obtain a set of discrete energy levels, Landau levels, right, which are separated by let's say an energy range which depends on the magnetic field. So as you are increasing the magnetic field, these levels will cross the Fermi energy, and so physics will change. And what happens in a real device is that you have a lateral confinement, and due to this confinement, actually the energy levels, so these Landau levels, as you are getting close to the edge, they are forced to, well, their energy is following the potential confinement potential, let's say. And so if, for instance, your Fermi energy is laying in between two Landau levels in the bulk of the system, then actually it will cross these Landau levels close to the edges, and this will give rise to these edge states that are, let's say, propagating in opposite different directions on both edges of the sample. And of course, to have backscattering in this situation, an electron that is propagating in this way should actually cross the whole sample to be, let's say, transported to the other side, and this is forbidden. So this is, let's say, a way to explain with the hands that these edge states are topologically protected, so there is no backscattering. On the contrary, if the Fermi energy is aligned with the Landau level, or if the Landau level is actually crossing the Fermi energy, then you have states that are populated in the bulk, and then you can have this transfer of charges from one side to the other, and you get some kind of normal resistive behavior that is easy to spot. So you have a finite resistance. Okay, so in practice, that's what you measure. So this is the resistance, the longitudinal resistance Rxx in green, and the transverse resistance Rxy. And what happens if you have the Fermi level in between two Landau levels in the bulk, then you are here. So you have zero resistance, zero longitudinal resistance, and you are on a plateau on the transverse resistance. So that's one of the examples here, but then it's as you are increasing the magnetic field, each Landau level is sweeping through the Fermi energy. And then on the contrary, if you have a Landau level crossing the Fermi energy, then you have finite resistance states and you have a conducting bulk. Okay. Now this, let's say, these edge states, one of the nice perspective with them is that these are channels which are very, let's say, immune to decoherence. So you have really ballistic transport over very long range and coherent transport. And so you can think about using these quantum Hall edge states a bit like you would use beams, well, optical beams, coherent like laser beams. And you can think about doing equivalent experiment as you do in optics, for instance, this Mach-Zehnder interferometer. So this is typically what you do with an optical beam. You add beam splitters, and so you can, if you have, let's say, an optical beam, it is partially transmitted and partially reflected, and then you recombine these two beams at another beam splitter, and then if you look, or if you detect what happens here, then you can see interferences, for instance, if you change a little bit the position of these mirrors here. So this is a very common experiment in optics, but then it's much more complicated to think about that with electrons. But people have done that I think for the first who have done that were in the group of Motti Heilblum in the Weizmann Institute, and that's the device layout. So they actually they are in the quantum Hall regime, so they apply a large perpendicular magnetic field, and so these lines here are the quantum Hall edge states. And due to their clever, let's say, engineering of device, they managed to have two different paths with actually beam splitters here, which are constituted by quantum point contacts. So these are small constrictions. And so you can have a probability for the electron beam to be transmitted and reflected here, and another beam splitter here. And then you can also change the length of the path of the electrons due to these, thanks to these lateral gates. So you can actually have all the ingredients of this Mach-Zehnder optical experiment, but with electrons. And indeed, if you're in a regime where you maintain the phase coherence over the whole path here, So this can be a few micrometer long. So you need at least, let's say, 10 micrometer of electronic coherence. Then you may see interferences. So this experiment was done, in this case, in this paper of 2003. It was done at 6 millikelvin. And that's the result. So they see these nice oscillations as a function both of the magnetic field and of these gate voltage, which plays the same role as the, let's say, the mirror that you would move. So this was a very nice result, and this opened a lot of perspectives, in particular because with these Mach-Zehnder interferometers, you can think about combining different interferometers, and if you do that in a clever way, you can, for instance, test Bell inequalities with this kind of things, or doing interferometry experiments with not only with electrons, but also in the fractional quantum Hall regime, and so on. And so this has led to a lot of interesting works. You can also think about quantum computing. So if you send, for instance, pulse charge here, or what is called a leviton, so which is this, let's say, a single electron excitation, which is adapted to this regime, then you can have a flying qubit, and then you can do some entanglement and so on. And so there are some concepts that can lead you to quantum computing with this kind of systems. Okay.
Benoit, one question.
Yeah.
On the image, on the data, you have the x-axis is also in time, in minutes.
Yeah, I think in this experiment, well, you see that the magnetic field here this is a very small scale, and actually they had a drift in the magnetic field, and they used that instead of really applying a current that would be the classical way of applying a magnetic field. They had a small drift that they could measure in their system, and so they actually measured the time and calibrated the magnetic field as a function of time, something like that. So it's just, I think, if I remember well, that's what they did. Because actually the magnetic field scale here is very small because the loop here is extremely large. So the Arnold-Bohm period, if you want, is very small in terms of magnetic field. So you need a very, let's say, precise source of current for applying or for tuning the magnetic field.
Okay.
Okay. So in the case of so this is for, let's say, conventional two-dimensional electron systems, classical, let's say, based on semiconductor heterostructures. Usually this was done in gallium arsenide. That was the best system, and it's, I think, still the best system for mobility and so on at very low temperature. But nevertheless, there is some limitation in terms of coherence. And this was evidenced in the last 10 years. And so even though you can reach coherence length of the order of 100 micron in these systems, you still have some perturbation that leads to decoherence, coupling between edge states, and so on. And people have been thinking about other schemes for realizing, let's say, for playing or realizing electron quantum optics experiments with in other ways or with other systems. And graphene has been a strong candidate for that for different reasons. One of the reasons is that due to the peculiar structure of graphene, and the fact that charge carriers obey the Dirac equation, you end up with a Landau spectrum where you actually have a larger gap between the first Landau levels here. So this is nice because then you have a perspective of observing quantum Hall effect at higher temperature. And this is a result already 13 years old by Novoselov, where he shows that you can actually have this quantization at room temperature, but in very high magnetic field though. But nevertheless, for gallium arsenide systems, you never can observe this kind of things. And actually, I think the largest or the highest temperature that was where quantum Hall regime was reached in this case was about 30 Kelvin. So that's the first point. The second thing is that you also can expect to have much smaller width of the edge states. So an experiment, this reference here, reports that the width of the edge states is around a few nanometers in the case of graphene, while it can reach the micrometer scale in gallium arsenide. So in this case, if you have large, very wide edge states, then you can expect to have much more capacitive coupling that will lead to decoherence. So this is another argument in favor of graphene. And then the last thing is that you can also play with another quantum degree of freedom, which is the Valley isospin, right? So this is another ingredient that you can somehow harness to develop new concepts for quantum computing or electron quantum optics. Okay. So this is, let's say, that's why on paper graphene seems attractive, but in the end, in the first days and up to, let's say, 2, 3, 4 years ago, it was quite difficult to find papers where you would have very high quality. I mean, at a quality that would be comparable to gallium arsenide systems, at least even in encapsulated graphene. So these van der Waals heterostructure, which we have HBN, graphene, HBN. And this changed a bit when people started to stack these heterostructures on top of graphite. And so what we wanted to understand was, is there any mechanism that actually leads to topological breakdown in graphene that is not well understood? And to do that, we used scanning gate microscopy. So that's our approach. So we wanted to see at the local scale if actually this picture of perfectly transmitted edge state is valid in the case of graphene, and if there are some mechanisms that could lead to perturbations here on the path of these edge states. So scanning gate microscopy has already been a bit introduced. So the idea is to have a tip, right? So a metallic tip that is scanning at some distance from the surface. So there is no tunneling current. Anyway, there is a barrier, so you prevents the tunneling current. And that's precisely why you use this scanning gate technique, because if you didn't have this barrier, then you could think about scanning tunneling microscopy. But yeah, here you are interested in transport, so you measure the transport as you are moving this tip. And this tip introduces an electrostatic perturbation in your electronic system. And so you are actually measuring or mapping the effect of this perturbation on transport. So we have a setup here to do that at millikelvin temperature and up to 15 Tesla here at UT Louvain. And so we have used that setup. So it's not at all a trivial experiment, because then doing this kind of things requires to align the tip with the device, and then you are somehow blind because you don't have an optical access to the cantilever. So you need other techniques to measure or to let's say to put a feedback on the position of the tip and so on. So these are experiments which are quite time consuming and take a lot of, let's say, energy and patience. So that's so for that you need very skilled PhD students. So the idea is, of course, here you are applying, for instance, a negative voltage, and this will induce a perturbation. And then if you think about this picture of Landau levels, then you can imagine that these Landau levels will also be bent upwards or downwards in energy, depending on the polarity of the tip voltage. All right. Then well, the first studies that we have done with this kind of setup was on 2D semiconductor systems. And in this case, we were patterning constrictions, because we were thinking, okay, maybe we can induce with the tip some sort of backscattering here, and so we can map that in real space. So we, moving the tip and examining what happens in the constriction, we indeed found a lot of different situations, but in summary, let's say what was happening here was something like this. So we had, we could either trigger direct backscattering of the edge states, or backscattering or tunneling through localized state induced, for instance, by a local defect, and then you would have edge states circulating around this defect, and then the tip would actually tune the tunneling between the edge states and this defect. So if you look at what's happening here in terms of Landau levels, then you would have here a kind of localized states and around this local maximum here, and then you tune the transmission here through this barrier with the tip, and then this induces contrast. So I won't detail too much these results, so you can have a look at these papers, well, this one, and there is a paper in Nature Communications in 2010 where these things are detailed. And anyway, I'll come back to that with the difference that we see with graphene. So let me now show you some data for graphene. And again, we started our work studying constrictions. So just by analogy with what we had done in gallium arsenide, we thought maybe it's a good idea to see if we can trigger something in the constriction. And so we asked our colleagues in Aachen to provide this kind of device. And actually they were working on that because they were investigating quantum conductance measurements in this kind of systems. So basically it's a heterostructure of boron nitride here in blue, and then one monolayer of graphene and a top boron nitride, which is relatively thin. Here we are using 20 nanometer thick boron nitride. And then we have lateral contacts. These are line contacts. And then we have a backgate that allows us to tune, well, to go either on the electron side, on the hole side, or yeah, so that's quite common now. The experiments were performed around 100 millikelvin in this case. And so we have this perpendicular magnetic field. So this is conventional transport. So the Dirac point is somewhere here on the right. And then if you apply magnetic field, like for instance, 14 Tesla here, you see that in the transverse conductance, you have plateaus here at quantized at 2e²/h here, another one here. And then in the longitudinal resistance, this coincides with zero resistance states. And in between these zero resistance states, you have finite resistance, right, with some fluctuations here on top. And what we have done first was to apply a backgate voltage such that we are on the verge of this rise of conductance here. And so the idea is to just measure the resistance as we are moving this perturbation. And to our surprise, we obtained this quite unexpected result. So instead of having just contrast here in the center of the constriction, so the dashed line here is the constriction, we had contrast all along here, the etched portion of the device. Okay, so we thought, okay, maybe there is something wrong with this device, but we couldn't understand what was going on, because if you have edge states propagating on this side, edge states propagating on this side, then what this image would suggest in the classical picture was that the tip would induce somehow backscattering between this side and this side. So this made no sense. So we repeated again this experiment with another sample, and again, well, this time it was around this position here. So again, on the nu equals -6 on the whole side, and then focusing on again an etched region, we had this set of circular features here, and in this case, we had these concentric fringes, a bit like here. And the center of these features was located, let's say, at some distance from the etched region, typically between 100 nanometer and 200 nanometer. So that's the phenomenology. We have tons of images like that, and we tried to figure out what was happening there. So the central question was, why do we have contrast at the edges rather than at the constriction as in gallium arsenide? And then reading the literature, we came up, well, we found this various papers reporting or suggesting that actually there should be inhomogeneous electric field in the case of graphene if you are in this configuration with a backgate here, the dielectric, typically silicon oxide, some hundred of, well, let's say 300 nanometer typically. And then this is an image that is the result of just electrostatics. And you see that let's say the Z component of the electric field is really inhomogeneous when you look at what's happening, for instance, the difference between the center of the graphene flake, which is here, and the edges. So there is, with this inhomogeneous distribution and this, as a result of electrostatics, you can expect that the confinement potential is not a simple, let's say, well that you would have in principle if you don't have a backgate, which applies, let's say, on which you apply a voltage. So as a result, several people, including, I think this was the first paper where this was suggested, Silvestrov and Efetov in this PRB, suggested that as a result of this inhomogeneous or these fringing fields, let's say, the potential would rather look like this. So you would have local minima of potential here as a result of this potential. And then the result is that if you have your Landau levels with this peculiar shape and you look at the Fermi energy, you can have a situation where the Fermi energy is crossing Landau levels twice close to one edge and twice close to the other edges. And so this means that you have here you have, let's say, the conventional quantum Hall edge states, and then you have these blue modes which are counter-propagating and are really close to the other ones here. And so the question was, is there any backscattering between these propagating edge states and the counter-propagating edge states, or the upstream modes? And there has been some, let's say, hints for this backscattering. In particular, in this paper by Marguerite and co-workers in Nature last year, where they imaged dissipation. So they have a special thermal probe, let's say, which is based on a nanosquid. And the image that they see here tells them about thermal dissipation close to the edges of a graphene device. And they see this contrast at the edges. So that's the first thing. And then they had also scanning gate. Well, they could use their nano squid as a gate also. So they could perform this kind of scanning gate experiment, but with not with such a detailed image, because the tip is quite big, and they couldn't go to very high magnetic field. So they weren't really in the fully quantized quantum Hall regime. So our aim was to kind of really look at the detailed mechanism that would couple these two types of modes, so up and downstream. And what we came up with this idea that actually we have antidotes in between. So these antidotes, it looks like this. So you have, imagine you have your peculiar Landau level with this shape here. If you have some impurity that raises locally the potential here, then you will have again an edge state that's circulating around this perturbation, and then you can have tunneling between the conventional edge states and the upstream modes here through this small antidote. And then what's happening here with the tip is that if you have this tip-induced potential, which is rather broad. Typically, we have like, even if the tip is sharp and has an apex of like 20 nanometer radius, you have a long range effect, which is typically 500 nanometer wide. And so as you are approaching your tip, at some point, what happens is that you're not only distorting the broad shape of these Landau levels, but you are also tuning what's happening in this antidot. And if this antidot is small enough, you have confinement, so you have discrete energy levels. And as you are approaching the tip, what's happening is that you have alternance of coincidence of these energy levels between these energy levels and the propagating modes. And in that case, you have tunneling, and so you have dissipation. So this gives rise to finite resistance. And so in between, you have Coulomb blockade, and you have no, you are really close to zero resistance. So that's what we think is happening. And indeed, well, to kind of be sure that something like this is involved, and Coulomb blockade in particular, we performed spectroscopy. Well, let's say we applied a finite current. So applying a larger current actually is something quite common if you want to probe energy level in a Coulomb blockaded quantum dot. And what happens if you increase the current and if you change the configurations of level, you have these Coulomb diamonds that appear. This is quite characteristic of this regime of transport. And then from this data, well, here it's a bit uncommon because we are moving the tip. We are not, but you can do that also with the tip at a fixed position, changing the tip voltage here, and then you get also these Coulomb diamonds. So you can get some information on precisely the confinement and some energy and capacitive coupling of this antidot. So that's that was first confirmation. And then we also wanted to have further confirmation through simulations. So to see if this picture was actually at least qualitatively in line with what we observe. And so we performed simulations using the quant simulation package, which is a very convenient and very easy to use tight binding simulation package. That's the reference if you want to know more about it. And so to simulate our system, we took as an input this potential, let's say. So we are focusing just on one part of our device, on one edge. We are on the whole side. So actually the potential is actually like this. So you are confining holes, and what is happening here is that you have the edge here on the right side, and so you have these propagating edge states here. And then as you are going inside the sample, you have this perturbation, which induces small circulating edge states here around. So that's represented here. And then as the Fermi energy crosses again the Landau level, you have this upstream mode somewhere here. So that's what we think is happening. So this is, of course, here we haven't any quantitative information on this potential precisely, but so the comparison with the simulation will only be qualitative. What do we simulate exactly? So again, these are experimental images, and what I'm going to show you is actually related to that. But so in the experiment, what we can do is scanning along a line here, for instance, crossing one of these circular features, and then changing the voltage on the tip. So, but continuously. So this is represented here. And you see these resonances, but now they are evolving in a parabolic way as you are changing the voltage, right? So this is quite typical again of these Coulomb oscillations. And then at some point you reach a plateau when you have what we think is a full backscattering of the different modes. So now if you put your tip at some distance on the graphene side, at some distance of the edge, and you change the voltage, you get this kind of let's say cross section through this to this mapping. You see some peaks. That's the Coulomb blockade peaks, and this is the resistance here is rising when you have full backscattering. Right, so this is the tunneling regime, and then here you are actually applying a large voltage on the tip so that you are backscattering your modes. And that's the result of the simulation. So with this system, I mean, what I have just shown you before, so with this potential, you can calculate the transmission. And you have again these sharp peaks and this very nice, let's say, qualitative comparison with the, or correspondence with the experiment here. Of course, the horizontal scale is not the same, but in this tight binding simulation, you don't have actually, well, I mean, you cannot expect to have, especially also because your potential is arbitrary, you don't expect to have quantitative correspondence. And then what is nice with this simulation is that you can really look at what's happening by plotting the density of current in real space. And so this is what's happening, for instance, at this peak. So you have the transmitted current here, then your quantum antidot here, and then you see that there is some transfer or some tunneling between the upstream mode and the transmitted mode. While when you are on the zero resistance state, this transmission is much less effective. And then here, if you go to very large change in local density induced by the tip, then you have a full reflection. So that's, let's say, that's the work that we have performed. And so I'll just summarize it here. So in a nutshell, we have shown that we have both up and downstream modes along the same edge in graphene. At least this is, we think that our measurement give a strong indication for that. We have examined in detail topological breakdown of this edge channel induced by the tip. And we have shown that actually scanning gate microscopy is a nice tool to induce this tunneling and to spot exactly where topological breakdown occurs. And this is also, well, as a connection with the former talk, this is also something that should also apply to other 2D materials which are submitted to this kind of fringing fields. So that was the meaning of my question for the last speaker. So this is actually now on, this work is on archive. And if you want to know more about what we are doing, what I mentioned in the beginning, the Klein tunneling, we have 2 papers and 2 more papers under review. And then we have also some other works on graphene quantum rings that you may have seen in nano lasers and PRP, and a lot of other papers on semiconducting 2D systems that you can have a look at if you're interested. So with that, I will thank you for your attention, and I can take any question if you want.
Thanks a lot, Benoit, for your interesting talk. Okay, so Jerónimo, he has a question.
Yes, thank you, Benoit, for the talk. It's really interesting. I'm wondering if you can tell us more about the nature of these sort of impurities. You gave like a nice explanation in terms of some discrete states for around this impurity potential. I wonder what happens if, for example, you have 1 or more than 2 electrons in this impurity state.
Yeah, well, actually, the nature of these impurities that give rise to this, let's say, small local maximum in the potential is still a topic of research. What we think is happening, may be happening, is that we have, for instance, locally local change in the electrostatic environment of graphene, and this may happen, for instance, if there are voids between graphene and HBN, and this can happen at the borders of the sample. And what we would like to do is to try to probe that with electrostatic force microscopy, because there has been 1 or 2 recent papers about that, showing that you can actually, even in encapsulated structure, map the electrostatic potential that is seen by electrons within the graphene. So that's for the reason why we have this inhomogeneous potential. But then, of course, we can confine, well, the number of electrons that we can confine in these antidotes depend on many parameters, on their size and so on. And we have seen really different behaviors. And in some cases, we have also not Coulomb diamonds, but we have rather kind of checkerboard pattern. So we can actually have interferences in these systems between different paths that are connected to these circulating edge states. So there are some interesting things to do with that, but this is still in progress, let's say.
Right. Now my second question is, the number of defects seems surprisingly low, right? I mean, you show an image where basically you have perhaps 1 defect, right?
Yeah, it depends on the scale, right? So if you still see my screen, right?
Yes.
Okay. Here you see that we have focused on 2 different defects, and the distance between them is typically a few hundred nanometer, right? So it's here you have 300–400 nanometer between them, and that's typically what we observe. But I cannot really, since we don't really know the reason or the origin of these defects, we cannot really have an idea, a more precise idea if this is something that is normal, that we can expect. So again, it's kind of they are spaced in well, by a few hundred nanometer, but actually the point is that maybe not all the perturbations of potential give rise to these antidotes. So what can happen is that we can have inhomogeneities in between here that do not give rise to an antidote, maybe because it's just below the Fermi level, or so the conditions to reach this confinement that give rise then to these circles is a bit peculiar. So maybe it's misleading just to count the number of defects just by counting the sets of circles. That's what I would say.
Right. Okay. Thank you.
Okay, thank you. We have a few extra questions in the chat window.
Let me see. Only that I don't see the chat window. I don't know why. You can maybe.
I can read it for you if you like also.
Yeah.
Okay, so the first question is from Reyes Calvo. She says, also, what is the role of spin and valley here? I expect at such a strong field, the Landau level to be spliced in spin and valley.
Well, actually, here we are not yet, in this case, this is not such a high quality graphene device. So in more recent devices, we would be actually indeed in the, we would have clearer indications that we are spin split and valley split, but actually here it wasn't the case. So you don't have intermediate filling factors here with, I mean, this is filling factor -2 and this is -6, and there is nothing in between. And there is no sign for additional, let's say, lifting degeneracy in between here. But indeed, that's something that we will consider in the next experiments.
Just out of curiosity, what's the magnitude of the voltage you apply to the tip?
Here it's very small. It's typically, well, it's really close to 0 volt. But in some cases, I don't know if they have the experiments here. Well, maybe I have it. Let me see. in the paper. We have some complementary data. Here you see we go from, this is +3 volts, 0 volt, and -6, so it's at the same position, right? So typically this is not enough to have, well, it can be a quite large perturbation, but yeah, well, we have, that's typical range that we apply, yeah.
Thank you.
There is another question by Matias Cubillos. He says, have antidotes been observed or predicted in other materials?
Well, in the case of, I think I have my older paper here. That was not, it's not this one. That's the paper on 2D electron systems. And we have actually the same kind of phenomenology in a mesoscopic device in the quantum Hall regime. And here again, we have, we invoked antidotes in this case. So, I mean, any perturbation of potential in this case will give rise to this, well, this inhomogeneous potential will then give rise to circulating edge states around it if you are in the right conditions. So you can actually, I think it's quite common.
Mm-hmm. Okay, I have a question myself. So it is a well-known effect, experimentally observed for quite a few years, that in graphene, when you apply mechanical strain, I mean, mechanical deformations, you get an effective magnetic field, right? I mean, it's like, so you get Landau levels, you know, just out of the strain.
Yeah.
So a question is, this effect does not interfere somehow in your experiments? I mean, how can you rule out the possibility that the graphene has some ripples, for example, when you prepare your samples? But
that's indeed a candidate for the origin of these some, well, inhomogeneities. But at this stage, I cannot tell you, I cannot rule out this possibility. So it's possible that it's related to that. But I think that it would be good to have a kind of control experiment where you induce strain locally and then look at this kind of quantum Hall physics in this case. So that would be very, very nice idea. But then you need really to work on the way to do it in practice, right? So it's a challenge.
Okay, thanks a lot. And is there any further questions from the audience?
Yeah, I do have a question, more practical, let's say, about the device. How many samples did you try or measure before for getting a few good ones? How do you screen the device? Do you first measure mobility?
Yeah, usually
mobility you need.
Yeah, usually we first measure mobility, but in this case, actually, we are limited because we received some devices from our colleagues in Aachen, and that's the same actually that we measured in different other papers. This is the paper on Klein tunneling, for instance, and we have like 2 or 3 good devices out of 10. So that's the problem is that in some devices the boron nitride layer was too thick, so the scanning gate was too far away from the graphene system. So that was one problem. But in terms of mobility, it was quite similar. I think we have always like I don't know if there is a number here, but it's typically yeah, it's below 100,000 centimeters squared per volt second, but I can in the range between 10,000 and 100,000, and they are all more or less in that range. So it's not exceptional, but it's quite common. And it's, the good thing is that it's very comparable to what has been done in many other groups between 2010 and 2020, let's say, at least for the devices without graphitic backgates, because there you really increase the mobility.
And the thickness of, like you said, the boron nitride could impact the measurement, and the quality also. I mean,
The quality, I'm not sure. Well, that's more the back. On the back sides, you need at least, let's say, 50 or at least 20, 30 nanometer distance between the graphene and the silicon oxide to have to reach a good mobility. But on the top side, it's not so critical. That's our experience. We didn't see much difference between the devices with a thick HBN overlayer or thin HBN overlayer.
Okay.
So it doesn't seem that, for instance, you could invoke electrostatic perturbation coming from the top surface, because then it would be different in different samples.
Okay, thank you, Benoit. Very nice talk, interesting. How can you cool the sample? You go down, those measurement, the coolest measurement was done at 20 millikelvin?
Yeah, well, what I gave in the presentation, 100 millikelvin is, in this case, is the electron temperature. We cool down typically to 25 millikelvin, but then the effective temperature is a bit higher. And we measure that with Coulomb blockade effect. You can extract it.
Okay, great, nice. Thank you.
Well, thank you very much, Benoit, again. I don't know if there's maybe one more question. I don't see any more in the chat. Okay, well, thanks a lot, Benoit.
Thanks
for
to you.
This interesting talk. Okay, so we continue with our next speaker, which is Dr. Vladimir Juricic. He's an assistant professor at the Nordic Institute for Theoretical Physics in Sweden. His expertise is in the theoretical condensed matter physics, studying electronic properties of quantum materials, such as graphene and topological materials in general. So we welcome Professor Juricic.
Thank you, Enrique. Thanks for the introduction and for the opportunity to present my recent work now on optical conductivity in topological metals. So let me share the screen. So yeah. Okay, yeah.
Perfect.
Great. So okay, good. So you see my here the pointer, right?
Yes.
Yeah, good. So okay, so this work actually has been done in collaboration with Professor Roy, who is at Lehigh University in the United States, and my colleague from Nordita, Professor Habib Rostami, and the talk is actually based on these two recent papers. So I will start by giving an introduction to topological semi-metal, and in particular, I will discuss how optical conductivity can be used as a universal probe of these systems. And then I will focus on two specific examples, namely the non-Fermi liquid emerging out of a quantum critical point of strongly interacting two-dimensional Dirac fermions. And then I will switch to nonlinear conductivity that turns out to be, in fact, useful for probing interacting tilted two-dimensional Dirac fermions, and then I will summarize. So this venture in topological metals, in fact, started by the discovery of graphene about 15 years ago, and as you all know, basically graphene features these massless Dirac fermions at the corners of the Brillouin zone, where the valence and the conduction band cross each other. And these are, in fact, protected, these crossing points, or this crossing between the valence and the conduction band is protected by the sublattice and time reversal symmetries. And later on, in fact, there was also sort of three-dimensional counterparts of graphene were discovered, and these constitute the so-called Dirac and Weil materials, where in fact strong spin orbit coupling together now with the breaking of either inversion symmetry or time reversal symmetry gives rise to a Weil semi-metal, while when the two of these symmetry are simultaneously preserved, then Dirac semi-metal is actually achieved, and these are some of the compounds where these new states of quantum matter have been realized. And that was actually the situation in about 2015, at least experimentally. So, but now, in fact, I would say that this age of these non-interacting states now actually has sort of passed, and now we enter the new era of actually interacting driven topological states, where in fact also is experimentally effects of the interactions have been observed, and in particular in this organic based material in 2 dimensions. So this is a 2-dimensional organic crystal where featuring tilted Dirac cones, the reshaping of these Dirac cones has been experimentally observed, and it has been interpreted in terms of the long-range Coulomb interaction. On the other hand, there recently in 3 dimensions, there was a report on the observation of so-called axionic insulator or axionic charge density wave in the Weil semi-metallic system. So you can see basically that this is this is seen in the transport measurement, where in fact where you see since this is inverse temperature, so basically after as you cross some critical temperature, you enter this insulating state with a finite, this finite resistivity, which is scales exponentially with the temperature, and presumably the slope of this scaling in fact gives you the gap in this system. So moreover, there was also, there were proposals, and that in fact there are other types of quasi-particles in condensed matter systems, where in fact this characteristic pseudo-Lorentz symmetry or pseudo-relativistic symmetry, as realized in graphene or in Weil and Dirac semi-metal, can be also absent, and this situation is in fact realized in some of the so-called multi-Weil semi-metals. And on the other hand, there is, as shown in this seminal paper, there is also a zoo of other so-called higher spin or fermions, where you have a crossing of more than 2 bands at the Fermi level. And one particular example of this is our so-called spin 3/2 birefringent fermions, which would, in the language of high energy physics, be called Rarita-Schwinger fermions. And they actually, and there are also other candidates or other emergent quasi-particles, such as spin 1 fermions that actually have no counterpart in the high energy physics. So on top of that, it's not only that now we have these new interesting quasi-particles, but in fact they produce some non-trivial effects. And some of these actually have been recently studied with my collaborators, and in particular, I'm interested in quantum critical behavior of this sort of Lorentz and non-Lorentz symmetry preserving quasi-particles, and their interaction effects, quantum critical behavior, and such. And also, on the other hand, also disorder produces very, very interesting effects, in particular in vile semi-metals, where it gives rise to an exotic quantum phase transitions that is actually different than conventional Anderson phase transition induced by disorder that we already know for more than 50 years now. And these new actually effects, these effects not only the bulk properties of these systems, but also their surface states, as you know, since you know that these vile topological semi-metals feature Fermi arcs because of these vile points in the bulk sourcing non-abelian, sourcing abelian Berry curvature, and these also give rise to non-trivial transfer behavior in the presence of disorder. And so other line of actually of my interest is in fact probing of nodal semi-metals. And today I will be talking about optical conductivity, but actually in collaboration with Enrique and Rodrigo, we have recently studied how in fact dislocation defects, which are ubiquitous crystalline defects in materials, can be used to probe this monopole charge or topological features of vile metals. And recently I also studied how in fact some sort of classical responses such as viscosity can be used to probe topological features in vile metals of of different with different dispersions, dimensionality, and so on. So, but today I will talk about optical conductivity, and I will start by setting up the framework within this Kubo formalism. So, where optical conductivity is directly related to current correlation, and in the limit. So when frequency is much greater than temperature, which I will be only talking about today, the details, in fact, of scattering mechanism do not matter. So and therefore, in this so-called collisionless regime, transport exhibits the universality, meaning that conductivity is and other even non-linear conductivity depend only on dimensionality, band dispersion, and electron-electron interactions in the system. And so one can in fact see this from a simple scaling argument starting from this Kubo formula. So we just recall that in fact, when we couple external electromagnetic field, it should couple with the current of the the matter in Lagrange invariant way. But on the other hand, we know that this vector potential, because it couples with pile substitution, so you just replace momentum with momentum plus the vector potential, the vector potential has to have the same scaling dimension as the momentum. And that, by simple power counting now, from this formula, because action is dimensionless, then you have actually that time or imaginary time has this scaling dimension of minus z, so in units of momentum, where z is the dynamical exponent, r is the measure here, so this is minus d, this is the engineering dimension of this of the measure of the spatial part, and then we have this number 1 here. So basically, to get this action to be dimensionless, current has to have d plus z minus 1 engineering dimension in the units of momentum or inverse length, if you wish. And so now basically you can just compute the scaling dimension of the Fourier transform of this correlation function in the real space, and then you can see that in fact there its scaling dimension is d plus z minus 2. And now just plug this in the Kubo formula. Omega has the scaling dimension of z, so you actually cancel out the z here, and you get the conductivity. So optical conductivity has this scaling dimension of d minus 2. So you see that basically here this scaling dimension depends only on the dimensionality of the system. So and now in fact one can write the scaling function for the optical conductivity in terms of frequency. So because again frequency has this scaling dimension of z, so we have this prefactor of omega to the power d minus 2 over z, and times, so and now we have this function which is a dimensionless function of dimensionless variables, which we choose basically with what we have at hand. So let's say we are at the finite temperature, finite frequency, finite chemical potential, we have interactions, so we form dimensionless combinations and we get this scaling function. And this is actually a very useful guide for actually exploration of optical conductivity in different systems. So now, again, I will now look at the interaction effects in graphene and how actually this quantum critical point that actually emerges in graphene at strong interaction can be probed by the optical conductivity. And so most important at this point for graphene is to actually remember that because of this linear dispersion, the density of states close to the Dirac point scales linearly with energy. So it vanishes at the Dirac point, but it does so linearly. So, and that in fact provides the protection from at weak interactions. However, at strong interactions, there can be instability. The Dirac fermions can undergo quantum phase transitions to either insulating or superconducting states, that depending on the nature of the interaction driving the instability. So for instance, if you consider Hubbard on-site repulsion, then in fact one can first just look at the mean field level, and then you can see that in fact there is a critical coupling for opening up the gap at the Dirac point, which is nothing but the relativistic mass for Dirac fermions. And as you can also see from here, that the gap in fact opens only above some critical interaction, which is non-universal. because it depends on the cutoff about which actually this linear approximation for Dirac fermions ceases to be applicable. And in fact, Dirac fermions in that way go quantum critical close to this transition. And the quantum critical theory, in fact, describing this transition is so-called Gross-Nouveau-Yukawa theory, where besides Dirac fermions, of massless Dirac fermions, we also have, of course, at this quantum critical region here, fluctuations from the coming from the order state, so coming from the vicinity of the order state, and now this also this fermionic massless excitations and the bosonic ones actually interact in this critical region, and they have to be taken into account simultaneously. And this is actually this is taken into account by considering this Yukawa coupling in this quantum critical theory. So one takes these three terms and then one can perform, in fact, this analysis of this theory. So one if you again look at the dimensionality of these couplings, you can see that they are marginal precisely in 3+1 space-time dimensions, or 3 spatial and of course 1 imaginary time. So we are looking here at the quantum phase transition at the 0 temperature. So we have to include, in fact, this imaginary time dimension. And to control now the, so now basically because the coupling is at the instability is at the strong coupling, you see, in D equal 2, both couplings actually are relevant. So they lead to a strong coupling instability, and one has to, in fact, then take, one has to actually, go beyond the mean field. So one has to actually seriously take into account the fluctuations. And one way to do that is to consider, to perform a randomization group analysis, and by taking this deviation from the upper critical dimension as the expansion parameter. And when one does so, so first of all, you can take the theory without any fermions, you get the standard Wilson-Fisher critical point, and then when you switch on the fermions and Yukawa coupling, this Wilson-Fisher critical point becomes unstable, and you end up with this so-called Gross-Nouveau-Yukawa critical point that controls this transition. And that in fact has been, we have shown about 10 years ago, and later actually this scenario has been confirmed in numerical studies of basically by using quantum Monte Carlo simulations of the Hubbard model on the honeycomb lattice. So what happens, in fact, close as you approach a quantum critical point by actually tuning the interaction, is that these Dirac fermions from the Dirac semi-metal become more and more incoherent, so they lose their quasi-particle nature and at this quantum critical point they completely cease to exist. So they're as well-defined sharp quasi-particle excitations, because their quasi-particle pole actually vanishes, while on the other hand, when you have this broken symmetry phase, for instance, an antiferromagnet, the corresponding spin waves actually are, in fact, the corresponding gap, the corresponding gap, in fact, vanishes as you approach the quantum critical point, while Fermi velocity, because this quantum critical point, in fact, is relativistic, so Z is equal to 1, so basically at this relativistic quantum critical point, you have a still linear scaling of frequency and momentum. Velocity, this Fermi velocity is actually non-critical, so by measuring Fermi velocity, you would never conclude that there is anything special going on here. So, but now let's turn to optical conductivity and see what happens with this observable. So as before, as announced before, so this the optical conductivity has this dimensionality of d-2, and in fact, in d equal 2 is the optical conductivity is dimensionless. So and so if you start with 3 Dirac fermions, in fact, you get you can in fact compute this universal optical conductivity, the full scaling function, and in the limit, you see in the limit when which we are interested in, this limit of collisionless limit where frequency is much greater than temperature, you get just a number. This is this NF times pi over 4, where NF counts the number of 4 component Dirac fermions in the system. So this so-called is interband part. So where you have actually scattering between conduction and valence band, while the Drude part actually has this perfect delta-like shape, right? Because here you are in the collisionless regime, so your scattering time is in fact infinite. And so now the question is, what happens now with this the optical conductivity when you're close to this quantum critical point? So in fact, one can address this problem by recalling that basically scaling of optical conductivity is intimately connected with the gauge invariance, and the gauge invariance together with the Lorentz invariance then implies that the current correlation function receives the correction only through this so-called self-energy. So in fact, the only effect of the interactions would be actually to make these Dirac fermions more anomalous close to this quantum critical point. And in fact, strictly at the quantum critical point, they would really vanish as, they would really cease to exist as really sharply defined quasi-particles. So now, when we are in this quantum critical regime that so basically emanates from this quantum critical point, and it extends up to finite temperatures, one can then compute this field, in fact, this wave function renormalization here, or field strength renormalization in the field theory language, and one can get that the interband part of the conductivity is in fact suppressed, and this suppression is, you see, scales as MB over NF, where MB is the number of these bosonic degrees of freedom. So basically number of order parameter components in the order phase, while NF is the number of 4 component Dirac fermions. And here actually we computed this to the leading order in epsilon, and the universal function, which is this h bar, which depends on, of course, this now h bar omega over kBt, is actually numerically computed and is shown here. So on the same footing, the Drude part also gets suppressed. So here, of course, because we are at in the collisionless regime, we cannot, by default, we cannot actually renormalize this delta function. So for that, actually, to smoothen out this delta function, you have to go beyond. So you have to include some scattering mechanism. But what we can do, what actually we get here only is that, in fact, the weight of this peak, in fact, is suppressed. So the weight of the Drude peak is suppressed by this coherent, by the scattering of this soup of the bosonic and fermionic excitations close to the quantum critical point. And so these should have implications for experiments. So we hope that, in fact, because of this, of the recent experiments on these organic 2D dimensional wild fermions, we hope actually that these effects will be seen there, and actually, I mean, if in fact this, for instance, if it was possible to drive this transition by Hubbard U, then we would expect to have this suppression of optical conductivity, and also, of course, in twisted bilayer graphene, there may be the transition may be governed by the by slow Dirac fermions, and in that case, this in the quantum critical region, similar suppression of the optical conductivity should be seen. So now let me just switch to actually nonlinear hold conductivity. So now we will look at the nonlinear transport, and we will look at the time reversal symmetric system. So now, as you have already heard today, I mean, we have this whole conductivity, which in fact characterizes the topological states, in 2 dimensions, but actually to have nonlinear this type of linear hold conductivity response, non-trivial, you have to break time reversal symmetry. However, if you go beyond and consider nonlinear hold conductivity, now because of, if you look at the structure of the current here, now you will have actually this barrier curvature dipole, which in fact now is itself odd under time reversal, and actually cancels out oddness of this Berry phase or Berry connection under time reversal. So in fact, you can have nonlinear conductivity as a response in time reversal symmetric systems. And this is in fact what we are going to use for probing actually tilted while or Dirac semi-metals in 2 dimensions. So why so? Because in fact, linear optical conductivity, let's say, the finite chemical potential would be finite in both. Even if you break the, let's say, inversion symmetry or sublattice symmetry, but in fact, the nonlinear response, nonlinear hold conductivity would be finite only in the inversion broken phase. And again, here one can look at the scaling, and in this collisionless regime, again, you in fact get the universal scaling behavior. So for the nth order conductivity, now the scaling will be 1 over omega times 2n minus d. So now in fact you see the order of the response in fact matters for the scaling function. And here we will only consider n equal 2, so the second order conductivity, and then we will look at the tilted Dirac fermions as for example observed in this organic compound experimentally. So this is so basically here is the inversion breaking term, which comes, let's say, which acts as a mass term for Dirac fermions, while the tilting term is just proportional to unity, but in fact comes with the explicit momentum dependence. So you can think of it as a momentum dependent chemical potential. So even before you actually look at the interactions, there are actually some non-trivial features, coming from the tilting in the nonlinear probe. So again, use this Kubo formalism to compute that, and you see that second order conductivity now has Berry curvature dipole here in its formula. So then you see now if you look at the different regimes, so now in the intra band regime you get this peak in the response. So this is the real part of the this second order Hall conductivity. While as you crank up this the tilting from 0 to 1. So at 1, in fact, this tilting becomes critical, and when it exceeds 1, the system enters to the so-called type 2 regime. So here, in fact, you start with the 2 resonances at omega, which is, so we fix omega, and we have actually, we tune chemical potential. So we have these 2 resonances here at chemical potential equal to omega, and the chemical potential equal half of the omega. And then as you crank up this tilting, then you see this resonance actually splits into a peak and a dip, and and then basically there is some critical tilt at which the 2 dips merge, and then you only actually in this intra-band regime you only get actually a large dip in the response. So and on the other hand, also because of this tilting, Fermi surface is deformed, and as a consequence of this deformation of the Fermi surface, so just to recall, when you have only untilted metal, Dirac metal, Fermi surface is circular, right? But here now you get ellipsoidal Fermi surface now when you have the tilt, and as a consequence of this distortion of the Fermi surface, the resonance, which is in the circular case Lorentzian, actually gets also deformed. So you get a non-Lorentzian shape in the resonance. So, but now, in fact, like these already, so already before you take into account the interactions, this nonlinear conductivity has interesting and non-trivial features in the tilting case. But now, if you consider the interaction problem, so let's say we now crank up Hubbard U and look at the quantum criticality in this case, one can actually see a few interesting non-trivial features. And the first one is, in fact, that this tilt that we have in the system actually remains unrenormalized. So the tilt just stays as it is, irrespective of the interactions. And as a consequence of this, you get a line of quantum critical points. So remember before, in the untilted case, we just had one line, one quantum critical point, which is Gross-Novo-Yukawa. Now with finite alpha, this actually Gross-Novo-Yukawa is like traveling together with this tilt. So it depends on basically now the quantum criticality also depends on where you are of this line of critical points. For instance, anomalous dimension, giving basically the rate of vanishing of this quasi-particle pole, Dirac quasi-particle pole, depends on alpha also, and also anomalous dimension for the bosonic excitation as well. And what is actually interesting is that also that actually this tilting increases the slope, decreases the slope at which actually these quasi particles actually vanish. So basically, as soon as you move from the zero chemical potential, you get more states at the finite energy than in the absence of the slope of the tilt. And that actually, in turn reflects in the fact that actually now the quantum critical point is at the weaker coupling than in the case of untilted cone. Finally, so all this in fact now has consequences to the nonlinear Hall conductivity. So in fact, now when you compute the nonlinear conductivity, again using the anomalous dimension, you in fact get that first of all, nonlinear Hall conductivity is suppressed. So there is no quantization of this nonlinear conductivity, and in fact, suppression is in fact tilt dependent, as you can see here. So it's directly related to the anomalous dimension of these Dirac fermions at the point where you are in this space of quantum critical points, and this suppression is in fact relative, of course, to the suppression to the Hall conductivity without any interactions. So this is actually here. You can see how in fact this suppression in fact is scaling with the tilting as you actually crank up the value of the tilting parameter. And so just to conclude, now I hope I convinced you that optical conductivity is actually a very powerful probe for different topological semi-metals, and also it can be used to probe actually different, in different dimensionalities. Here I only discussed 2 dimensions, but in fact one can look at the 3-dimensional Weyl semi-metals and basically see that there as well, you get this non-trivial scaling behavior, etc. More specifically, for strongly coupled 2-dimensional Dirac liquid, we see that the collisionless optical conductivity is suppressed because of this strongly coupled soup of fermionic and bosonic excitations close to quantum critical point. And finally, the second order Hall conductivity also is sensitive to the interactions and to the tilt when actually you have this interacting now tilted gap Dirac fermions. And I think now at this stage, certainly more experiments are needed, in fact, to look for the interaction effects in topological metals. So thank you very much for your attention, and I'm happy to take your questions.
Thank you very much, Vladimir, for this interesting talk. And so we're open for questions from the audience. Well, I mean, to start, I have a question myself, Vladimir, regarding the effect of interactions in the optical conductivity, because
yes,
you're mentioning the role of Coulomb interactions among the fermions.
Yes.
What's your take on the role that the electron phonon coupling may have in those systems? Thinking about, for example, acoustic phonons.
Yes.
What's your take on that? I mean, what would you expect?
Well, I would look. I mean, I would expect actually if you start, with let's say with let's say you couple phonon field with the with the bilinear, with the Dirac fermion bilinear, then you would actually get in the weak coupling regime. Let's say, close to, the semi-metallic ground state, when this coupling is not too strong, let's say, definitely you will get a suppression of the conductivity, but this suppression, would actually be scaling, because this is a short-range interaction, and then, so I would expect that, that basically, this short-range interaction has some, from the point of view of the engineering dimension, let's say, that this interaction would be irrelevant. So so you would actually get some power law. I mean, depending on specifically on the interaction, but in general, it would produce some a power law suppression of the optical conductivity, right, close to the semi-metallic phase. So this, in fact, would be sort of on the same footing as as if you were to consider suppression of the optical conductivity coming from the short-range interaction, but close to the semi-metallic ground state. So here we looked at the suppression close to the quantum critical point, which is different problem. There, right, there you would just have, because this interaction would be has the scaling dimension equal to 1, and you would get actually correction to conductivity scaling linearly with omega, which ultimately would vanish at omega equals 0, but at any finite omega you would get actually correction, a finite correction.
Okay, thank you. Do you have any other questions? Well, it seems there are not more questions. So thank you again very much, Vladimir, for the nice talk.
Thank you, Enrico. Thank you very much. Yes.
So our final speaker for the session of this morning will be Dr. Diana Dulich. She's an associate professor in the Department of Physics at the Universidad de Chile. She works on molecular electronics, in charge transport in nanoscopic devices. So we welcome Diana for the next talk.
Is there another? Oh, there it is.
Diana, we cannot hear you.
Yeah. Can you hear me?
Yeah, now I can hear you.
Oh, okay. Well, I had a long speech. I will do it again. Yeah. Well, where is now my presentation? Yeah. So you hear me, right?
Yes, now we can hear you.
Okay, so now everything. No, I just said that I would like to thank the organizers for inviting me, and especially Loic and Enrique, and that I'm really glad that you obtained these funds, and that I wish you the best luck with your especially in this hard, difficult condition, yeah, to initiate something. And today, well, I'm going to talk about my work, and I will switch for previous talks that were, well, transport in 2 dimensions. I will talk about transport in 0 dimension, and in fact, transport on a single molecular scale. And in particular, I will actually present 10 years work of mine, and you will see many people that helped. And I will try, well, to convince you. Well, I will try to show you what is necessary to actually measure transport on a single molecular scale in a really reliable way. Yeah, and the title is Designing of a Perfect Molecule for the Mechanically Controllable Break Junction Experiment. And I was really lucky to work with many really great chemists. And all I want to say is that without really very, very good chemist devoted to collaboration with people doing transport measurements and designing the molecules, especially for our experiments. There is nothing that that we can achieve. I mean, just measuring whatever kind of molecules is not enough to really get a good and interesting transport measurements. So, as I said, I will present the work that we started in Delft in 2010, that I initiated Delft, work on porphyrins. And as you can see, there were many people, both from Delft and both my group here, working on the transport on the break junction measurements. There were a lot of chemists involved in the project because we measured many different kinds of molecules, and also we often have theoreticians on the project that are giving us prediction and results. And okay, here is the basically the team that is that was involved in measurements that are in this presentation, and our last basically chemical collaboration on porphyrins with Marcel Mayor and his student Patrick actually really gave us really nice results, and we are not going to change basically our chemistry, which we did in the past 10 years. So, okay, first of all, why porphyrin molecules? Yeah. Porphyrin molecules are very interesting in, well, for transport measurements because they are highly conjugated, so they are conducting, and they have many important roles in our organism, in bio-inspired, let's say, molecular design. They have architectural flexibility. We can make also diodes and all kind of potential electronic single molecular electronic devices. They are stable, so in principle they can give reliable results, and they can attach to surfaces or electrodes, which we need in order to do our experiments. And of course they have a very interesting optical properties. They are from the point of view of functional molecular electronics, they are very, very interesting molecules. So if we want to attach a molecule which is an entity of 1-2 nanometers size, as you can imagine, it's not so trivial. So we have to attach it with the electrodes which are appropriate for attachment to such a small entity. And for years, it took a long time actually to understand the basic transport properties on a single molecular scale. And these are, for instance, how to reliably connect the molecule to the electrodes. Also, how do we know that we have only one and not a bunch of molecules in between our electrodes? Do we influence, and how do we influence the contact how the contact between the molecule and electrode influence our transport measurements, and if we have a functional molecule, how does that influence the functionalities in our molecule? Yeah. And these things were really essential to understand in order to do a more advanced transport measurement, or if you want to say in order to really manipulate transport in a molecule with external stimuli. And this external stimuli can be electrostatic gate or light or magnetic field or mechanical tuning. So there are molecules which on paper or just by the design should have all these kind of things that you can actually change and manipulate. However, if you don't control this first basic part, you can really not say much about the transport or about the really whether the influence that you wanted to apply to a molecule is due to the changing in functionalities, or is it just the artifact of the experiment? So now, after, well, basically 20 years of advances of a single of the break junction experiment in on a single molecular level, we can say that we know really how to control this experiment and how to address the whole problem. I'm going to talk about my expertise, and that is mechanically controllable break junction technique. Many people, much more people use actually STM break junction technique, which is now the STM tip and measuring in solution and getting conductance of a molecule, and then for a huge number of molecules, so statistic. However, I'm going to talk about mechanically controllable break junction technique, which is basically that we fabricate electrodes on the top of a polymer substrate, then we etch the polymer, and we have a free standing bridge like this metal bridge. We can also make devices with the gate, so then have a transistor geometry. And at the beginning of the field, our measurements were just much slower than STM, because we were mechanically with the motor bending these electrodes and opening and closing our device with the molecules in between that are deposited in a dry condition and attached via this tile end groups to our gold. And when we did that, the experiments that way, we could have maybe 100 traces, which is not enough to build a sufficiently good statistic. However, since maybe 10 years ago, we are doing experiments with piezo, so we also have a very fast statistic, and the advantage of our measurements is also that we can include the gate into our devices, and that we have a superior stability of our junction. That means that we can control the spacing with 10 picometers regime, and we can also at room temperature stand in that position without moving for hours. So meaning that this technique is very, very good for basically doing IV spectroscopy which one cannot get in the STM regime, break junction regime, or it's much more difficult or less stable. Yeah. What do we do? As I said, we bend the substrate, so we stretch this gold neck. And at the beginning, we are measuring the bulk gold conduction, but as we stretch the junction, we are forming a narrow neck here, and what we see in our conductance measurement, we see that the conductance is going down, and that when we get into a quantum regime, that we have just a few channels here, terminating with only one conducting channel, that we observe the quantum conductance. And after having this 1G node, the quantum conductance value plateau, our junction breaks in abrupt way, and then here we see a tunneling. So this is what we see when we just stretch, when we don't have any molecules inside of our junction. And now if we do that histograms, and we can build in conductance, and we can get a one-dimensional histogram where we see a peak whenever we saw a plateau. So here you see 1G naught peak collected from many traces that we obtain, or we can basically get information also about the spacing between electrodes, or the time that it takes to stretch a molecule, by putting all this conductance tracing on the top of each other. And then we have this color histogram, and you see here we see the tunneling, and so this is basically what molecule inside. And now if we put in between the molecule by the stylus group attach to our electron, we what we see, and you will see that it's not always the case, is that when we have a molecule attached within electrodes, we will observe here yet another peak, and then which will yet another plateau, which will result in the peak in our statistical measurements. And indeed, here is here is the molecule, porphyrin molecule, and the two corresponding histograms. And for this, designed by Marcel Mayor and actually Patrick with my suggestion, and you will see that this molecule is actually doing exactly what we want. It has a very pronounced peak here at value 10 to the -4, which is a kind of ideal picture of a single molecule transport. Because for any application, it is also important that the molecule has a high conduction, because if we want to do any changes with external influence on the molecule, we need to see a molecule in our measuring range, which is basically up to 10 to the -7. Well, now a student in Delft, PhD student, actually developed electronics to go even two orders of magnitude lower. But so you see, whatever change you want to observe, you really want to see the change in your measuring window, because if it's too low, we cannot see anything. And this is now just an example how stable this measurement is. This is just a one trace conductance versus time, or let's say self-breaking. So you can see that we can form very stable molecular junctions, and that indeed in this regime we can actually observe any kind of changes that we want to study.
Jana?
Okay. Yes. Is somebody want?
In your previous slide,
Yeah.
can you comment about the size of the molecule? There's like a square part and also some arms to the sizes. So
Yeah. It's about 1.8 nanometers a molecule.
which part?
Well, this part that is relevant for our measurements, because for our measurements, I mean, you will see presentation. These are our very recent results. I will show you how we started, and that it took basically 10 years to come to this design.
Okay, thank you.
But we care about this size. We care about this size from tile to tile, because they will attach to the electrodes. And this part, you see these bulky groups that are specially designed that this part never actually attached to gold. And that is the whole trick. Yeah?
Okay, thank you.
Yeah. Okay, so but you will see. So this is the work from other groups on porphyrins, and well, basically many things are measured, but actually they do not produce such a nice plateaus, and they have a typically lower conductance, 10 to the minus 5. And so, as I mentioned, now, I mean, for already.
Could you make it bigger? Because I really cannot see if you could put the presentation mode, or I don't know. Just.
It is not in presentation mode. Oh, okay. Yeah, do you see it now?
Yes.
Yes, now we see it in full screen.
Better, thanks.
Yeah. Okay, I'm sorry. Yeah. So yeah, basically the porphyrin studied in literature were not really such well, reliable candidates actually for really going a step further for studying really functionalities, because the conductance was low, and they also gave various values of the conductance, which means that you do not have a controlled situation. Indeed, our first measurement in 2011 of a porphyrin molecule looked really bad, and as you can see, now we have conductance all over the place. So actually, and we tried many designs, because also tried to put the pyridine arms to try. So what we figured out that because porphyrin like to pi stack on surfaces, that actually we cannot really attach it in such a controlled way via tiles, but we can probe in our measurements all kind of configurations of porphyrin, and we tried various things, 1 arm, 2 arms, and all our results were well, very scattered. And so, I mean, that was a kind of disappointment at the beginning, but that's just life. So that was the conclusion was that with porphyrin molecules, it is the way it is. These porphyrin molecules, it is very difficult to actually have a controlled experiments and only one configuration. Therefore, our conductance measurements are just not enough to understand the transport in these molecules. As I mentioned, we are lucky with the mechanically controllable Bray junction that we can also measure IV characteristics, right? Because we have this stable junction, we can open the junction with a molecule and we can fix the electrodes and be there for a very, very long time, and then change the distance and measure IVs. And now if we just have a tunneling to electrodes, we see just vacuum tunneling explained in this model. So more or less, we see a kind of really shapeless curves that change by changing the distance. And now in the multiple model where we have a weak coupling, which is also important, we can see something as a Coulomb blockade. So we just see the transport where when the Fermi level of our electrodes aligns with the molecular level. Of course, in two-terminal geometry, all we can see is just the level that is the nearest to a Fermi level. We don't see more than that. But also, I must say that it's not always that we see this kind of a nice step that comes from the weak coupling, and that the problem can get even worse if we have a strong coupling, because then the transport of a molecule looks more or less similar to transport without molecule, because we lose this shape here. So, okay, these are now transport measurement on one of our porphyrin molecules, and you see this is vacuum tunneling. I mean, this is nice. And you can see, well, another thing that shows how much, how important is well, that you can also do IVs, is that you have these two curves from different distances that are basically have a completely different shape, but that here, if you would do a low bias conductance like we do for our opening and closing, that the value is the same. So it is really important for complex molecules that you can also do IV spectroscopy, and this is what we did basically, and we did a lot of statistics, and what we actually observed is that we can mechanically tune the gap in our porphyrin molecules. So you see, this is IV characteristic, this is differential conductance, and this is no molecules. So we observed that in these zinc porphyrin molecules, we can actually, if we push the electrodes in, that we can actually reduce the gap, and that we can do this repetitively for many times, and that in many different samples. And okay, that was work done actually, well, 10 years ago, but we wanted to understand that. We, of course, as I mentioned, you don't know if this resonance that you see, whether is HOMO or whether is LUMO. We wanted to understand why is that, and therefore we fabricated 3-terminal devices, because in this mode you actually by sweeping a gate voltage, we could say whether we have a transport through HOMO and LUMO. And basically what we observed that we can get, because of the different configuration that I showed you, that we can get both transport via HOMO and LUMO, but in both cases we always see this reduction of the gap by pushing the electrodes in. And so we always see that, and we had basically Chris Versailles, our theoretician that worked more than a year on this calculation, and that that he actually concluded that this shift can be attributed to formation of static and dynamic image charges. And okay, this was a very important experimental finding, because theoreticians usually to match the values with the experiments, actually they were always putting that into their calculation, and this was the first experiment actually showing that is really true. Yeah. Okay, we learned about sticking of porphyrin and so on, and so we wanted, well, I never quit well, the idea to study functional molecules and porphyrins, but now with this knowledge obtained in our first set of measurements with porphyrins, we knew that we somehow have to prevent the porphyrin body or to stick to our surface. So I talked to John Hill from that is in Tsukuba, Japan, and he said, well, I have a very interesting molecule, and okay, I said it has to be designed like this, so it should change the conductance if you pull this this central part, nitrogens, and it should change the conductance, and maybe you could see that in a branch experiments. And I said, okay, that is great. So well, this is the molecule. So he put two arms that in principle that have tiles here that should attach, and all we want to see is changes in conductance. However, our first molecule, first design, actually looked like this. Basically, we didn't see anything, really anything. And then we thought, okay, why would that be? And then we realized that maybe these arms are too short and the molecule is too bulky, so we can never reach these tiles in our experiment. Okay, so what did he do? He actually made the arms longer. So he made 4 phenyl rings, and indeed we got well, we got some plateaus in conductance, and however we didn't go. We got traces that are really decreasing conductance by stretching, but we also got things that have these different plateaus, and you see this is all around the place. So I mean, we showed that we can that we can manipulate conductance, but this is not, so we also had the reference molecules where we do not pull this nitrogen here, but we pull on the side where we do not see these changes in conductance. However, in this one, we see 2 peaks. So you see, again, it's not really ideal for studying this changes. The molecules are not ideal yet for studying this kind of changes. Well, after obtaining these results, I was really hunted with the thing that we should that somebody should make a molecule that has this group and only one of these group, because I thought that these two phenyls are actually these two things, and that the molecule also can stick on to that one. And it turns out that that synthesis is not so so easy, because I didn't get the right molecule until, okay, so this is yeah, this is stretching. So this was our conclusion. We can stretch it and the conductance go down. So we improved our system and got a bit more control by putting these groups on the porphyrin itself. But actually, we didn't have a yet ideal system, because even our references were not so good, and also because the conductance is going down. And I was talking about these results to Marcel Mayor, and I said, well, Marcel, this is nice, but it is not enough. Maybe it would be nice to have a molecule that where actually we see increase in the conductance. And little that I know, he thought about that, and basically he put his student Patrick to do a whole PhD on synthesizing this molecule, and he came with a molecule like that, where the idea is that now we attach it on this side and that side, and we stretch the molecule, and when these porphyrins start to align, that we should see the increase in the molecule. And I was in Delft at that point. Patrick came with the molecule, and again, this is the first result that we see. So conductance all over the place, and so on. And then I asked Patrick. Well, I explained to him what I would like to see as a molecule, and I said that I think that one would not stick. And Patrick is amazing chemist, and well, Marcel also, and it took him only a month to design the molecule that I asked other chemists for 2 years to make. And well, you see the result. It really did work, and we actually managed to get a very high conductance and very well-defined conductance. And it's so nice that is comparable to these linear molecules that most of the people are measuring, due to the fact that they give a very high conductance values. Okay, so not only that he made one molecule, he made a series of molecules that were with the different groups to see which one is giving us better results. So you see here we have 2, here we have 1, and also we also one with only one attachment, and so on. So you see that they more or less look the conductance is similar, and they look pretty nice. And in the meantime, we also started working on understanding our data better. So we started really taking 10,000s of traces and doing clustering to see in this, let's say, a bunch of 10,000 opening traces, is there only one peak that you see like this visually, or do we have some other structure and peaks hidden in this in the data? And basically we now can, well, we can say actually how many classes we have, and we are doing now standard for all our measurements. And in the case of porphyrin, we actually identified 3 classes, and by the chemical studies that I just show you, we actually identified that we see the transport, indeed, what we expect, but that we can also see attachment in other classes via this triple bond or attachment like this. So yeah, it is very tricky, and this is the way it is, because the molecule likes well to it's a molecule, and we cannot really control the nature, but at least we understand how does that work. Of course, Patrick used this design with putting triple bond and phenyl, and also masking these phenyls here, and he made a new molecule that similar to one that I showed, that gave very ambiguous results. And now we expected this conductance. I also asked him, he made this molecule with the same central part where we actually expect switching with UV light and oxidation and reduction. We have this molecule, but Luca is working in really developing a liquid cell in Delta, and this is already these things take a year or longer, because measuring in liquid we have to cover the sample, and it's much more difficult, but we are working on it, and it is going very well. But okay, I will show you that the new thing from Patrick actually really work well. And you see, this is a very big molecules, and you see well-defined conductance, and in fact this is something that is going to be a cover. This molecule is going to be a cover in the next I am in the next edition of a Journal of Organic Chemistry. So this is just a synthetic paper with some of the transfer measurements. But what I can say is that we actually really see some kind of oscillation in single traces, and basically I'm not going to show that this is that we see modulation when we do not the break measurement, but when we stay in one position and modulate the junction, molecular junction, that we see oscillation, and that, well, which are some kind of quantum interference. But I'm not going to talk about that, because since May we have Fabian Pauli on the team with his postdoc Katavura and his student Werner, and they are actually trying to, well, they are twisting the molecule and doing all kind of things, and they are trying to explain these observations of ours. And okay, this is now the other molecule that we are going to use in electrochemical measurement. And you see, again, we see in a dry state, we see a nice conductance, but we are really busy with well, Luca is busy with improving electronics and really and devices to be able to measure in liquid. Okay, my conclusion is that molecular electronic and studying complex and functional molecules is possible, but that it takes time. It takes a lot of people involved in the project because it takes collaboration with chemists that are really devoted to the project and really designing especially for our experiment. And I must say that I'm very, very lucky, well, to work with a group of Here van der Sand, because we put all efforts with people in Chile and with people in Delft to measure in parallel and to put this field to a higher level, and also to all the chemists, but especially Marcel and Patrick, that are just amazing in making the molecules. And yeah, and this work is really a joint work, and I want to thank this this dream of Averand and Ratner, molecular electronics, and I would call it in this case porphyronics, or porphyrin-based molecular electronics. And again, I want to thank people that contributed to this work by measuring synthesis and so on. And I want to thank you for your attention. Yeah. Questions?
Thank you very much, Diana, for this nice presentation. So, questions from the participants?
I have a question, Enrique.
Yes, please go ahead, Carolina.
Yeah.
Diana, what you mentioned that it's very tricky to design these molecules, right? So
yeah,
what are the requirements these molecules have to fulfill to be a good candidate for these experiments in molecular electronics? Because you're looking for stability at the junction, conductivity, but how do you, I mean, if you're looking for the next molecule, you know, it's for this.
What would be, well, the trick is that it has a very well defined conductance, and that also has a conductance which is higher than 10 to the minus 5, because basically most of the molecule, and that's why the field is really going down, because whatever molecule you put, you measure conductance and it's 10 to the minus 5. That's not very good conductor. Yeah. So you need really 10 to the minus 4 or so on. So basically nobody except us dares to do a molecule complex than linear, but this is because it also required chemistry that is a kind of, because you also don't want, you want only one peak and not more peaks, and to do that you have to put a bulky group on each phenyl, so these things are getting very complex. Yeah. But now, for instance, we can also make diodes. Hello? Did you hear me?
Yeah.
Yeah.
I heard you.
Yes.
But it has to do with geometry too, right?
Yeah.
And,
yeah.
Sorry?
Yeah.
I was asking about the geometry of the molecules, and also what about the contact? I mean the electrode, because you can modify that too, right? It's another path to improve the performance, right?
Well, the electrodes you cannot really modify because they always come as a product of breaking the junction. You can change the material, yes, to make it from other material. And that we don't do because everything except gold can also oxidize or something, yeah, and then give you, but of course, I mean, what they do in Delft, they also do a graphene break junction. Yeah, so you can do break junction experiment with graphene, but it turns out that these electrodes are not so good for molecules because also then, I mean, they have a very nice work just on that. So because you can see this, if you put pi stacking then between graphene sheets, you can really observe that in the measurements. Yeah. But when you put molecule on something like that, you have a much more complex system than if you are doing it with gold. Yeah.
For sure. Thanks. Thanks.
And
Diana, one question.
yeah.
Could it be that?
Tell me.
Yes, could it be that still you have to explore the different conduction channels on the molecule? For example,
Yeah,
have you
yeah,
tried to explore with a laser? Because sometimes these electron wave functions on the molecules spread out, for example, if you excite the molecule. So perhaps measuring the conductance at the same time you excite the molecule could enhance the conductivity, don't you think?
No, exactly, Geronimo, but that's the whole point. That's what we want to do because, you know, the molecule that we unfortunately have to measure in liquid cell, which is a work of 2 years with the special electronic people and so on. We want exactly to excite it. So in order to change from conducting to no conduct, and plus to put a gate. So we have a molecule, but we still didn't. We are still working on an experiment because. But as I said, if you don't have a starting molecule super reliable and you start shining something, you don't know what's going on.
Okay. Yes.
So we are basically now at the phase start really doing something with the functionalities, but that took 10 years. Yeah. That is the point. And people, normal people, not me, they don't want to bother to do that because it's really, really tough work. And not only that, you not only have somebody crazy enough like me, because to me, if it's not, if I don't see functionality, then I don't care about the simple molecules. But also you have to have crazy chemists. And my friend Marcel Mayor is my very good friend because he's as crazy as me. And then he puts a PhD student on that, and then the guy works for 4 years only on this molecule, yeah? And also I have other crazy friends here, but he has 20 molecules, so it's not, but there is always student in Delft and now postdoc working on this project. So we are just working with the team everywhere just to try to put the field to the next level. Yeah, so it's an international thing because we all believe that the field is down, not because there is something wrong with the field, but because many people don't want to put enough effort to do it right. So, but I believe it's possible, yeah? That is the point, yeah. And I hope I showed to you that, yeah, that you can see the progress in that business, but it's a hard work. Yeah.
Okay.
And I now have students here only doing clustering. I have students because they cannot work in the lab. I mean, I have collaboration with Marcos Orchard, who is a computational guy and with images, and we want to develop a better algorithm for clustering to explain break junction data. Yeah, so yeah, so
Diana, I have another question myself, if you don't mind. So what's the current status of the study of the Kondo resonant effect in the conductance of single molecule junctions?
Let me see. Well, we are not doing that. I'm not doing that too much, but Jerez group is, because, of course, I mean, here I don't have a low temperature measurement, right. Yeah, and the magnet, and they do have, but they don't do it in this kind of break junction experiment. They do it in a case of electromigrated samples. So they make electrodes via electromigration, and then they deposit molecules. And then if you have, magnetic molecules, you see all kind of Kondo, but you see all kind of very nice lines that they can Rajba, whatever. That part I think you would like more than my talk on conductance. No. But no, I understand that would be completely in line with the previous 3 talks, and it is possible, but it's a different experiment, and they are doing that with the magnetic molecules from Spain. There are a few groups, yeah, but I'm not working on that. And no, they are also doing nice work in publishing. Problem with this experiment is that you have your electrodes electro-burned, and then you deposit molecules, and then you have on 30 devices you have a yield of 2-3%, yeah. Mm-hmm. And then you go and measure at low temperatures, and even then it's not that each molecule connected in the same way that you see the same performance. So these experiments are really frustrating. And but they are nice. They can see these Coulomb diamonds with all kind of small lines that then they can explain, with theory and so on. But it's a very tough work.
Mm. Yeah, I mean, I worked myself for some time in these theoretical problems in collaboration with people at Rice, but it's been a while since I haven't gone back to the field. That's why I was asking if there is any further progress on that.
No, but the whole field is a bit down because, as I said, you can put a new molecule, but if you don't really see functionality, people are not really excited. You say, well, I put this molecule and that one has conductance 10⁻⁵, but the other one also, and then you say, but who cares? So that people start hearing, you have to do something better and something that you can change, and that you can show that you can more or less control or understand, and that's what we are trying to do. Yeah.
Okay. Thank you very much.
Thank you for inviting me.
Is there any other questions for Diana?
Yeah, I have a simple question. You didn't show transistor configuration measurement. Do you perform in Chile this kind of measurement?
Like, I mean, even making the gated device is very difficult.
Difficult, yeah, okay.
It's only that Michael and me could do it, and nowadays in Delft, all the younger people never even went into that. Yeah.
Mm.
Because you see, you have to, I mean, you have a gate that is hanging with the EVL, yeah, it's and then you need it when you bend it that it doesn't break and it doesn't leak. So anyhow, it's not a very good gate, yeah, because you have leakage. You cannot put more than 1.82 volts on the gate because it leaks.
Mm-hmm.
And also you can break the gate. And also it's not clear that the coupling of the molecule to the gate it's not very close also.
Mm-hmm. Okay.
So nobody dared to do that. And also you need a low temperature measurement, so it's beyond the possibilities to do it in Chile, yeah, I would say.
Okay, thank you. We can dream of that. Just let's hope that when
Yeah, you do. If I need it, I will do it in Delft. Yeah, because it. Yeah, but as I said, none of the students after Michael left and finished his PhD, none of the other people even dare to do that.
yeah.
Well,
Thank
okay.
you for your presentation.
Well, thank you again, Diana, and thank you again to all the speakers, all our guest speakers today for their nice talks. I would thank you again, all the participants, all the audience for their attention. And with that, I will close this first session of our webinar. I hope to see you all again on Thursday for our second session, which will start at 2 p.m. Santiago time. And have you all a nice afternoon for Europe, evening perhaps, and a nice day in Chile.
Yeah.
Thanks to all.
Thank you. Yeah.
Okay, thanks.
Bye. Hola, Arturo.
Bye.
Hi, hola.
¿Todo bien?
Sí, profesor, todo bien por acá.
Bueno, ya.
¿Cómo han
Hola,
estado
Loic.
ustedes?
Me disculpa, llámame por teléfono cuando terminas.
Ya, vale.
Porque
Ya,
tuviste... Ok. Chao.
Chao. Gracias.
Hasta luego.
Chao, Jerónimo.
Chao, Loic, que estés
Me
bien.
vas a extrañar, que estaba feliz de ver tu cara en vivo.
Por supuesto, me imagino que...
Hay que salir a ir a tomar hay que hablar de ciencia con cerveza, ¿no?
Oye, sí, me parece. Hace mucho tiempo que no hemos hablado no hemos hecho ningún seminario de fluidos, nada.
Pero Jerónimo, ¿tú tienes derecho de salir o no de tu casa?
Sí, por supuesto, la otra vez fui a ayudar a un postdoc que está sacando su carnet de identidad, ¿ya?
Yeah.
Y fui a entregarle una ayuda económica y ahí pasamos a un lugar de Ñuñoa.
¿Así?
Sí, así que nos tomamos una cervecita y unas papitas, pero fue difícil con la mascarilla.
Sí, me imagino, sí. Pero eso se puede manejar, o sea, después de 5 cervezas, la desinfección con el etanol funciona y no pasa nada.
Claro.
Yo creo que sí, a nuestra edad todavía no está grave este virus.
Todavía podemos sobrevivir.
Ya, eso.
Nos vemos el jueves. Jueves en la tarde.
El jueves.